let's do an example trying to find the maximum minimum of this problem and solve the constraints. Anyway, so what I want to do is I want to find two positive numbers whose sum is 190 and whose product is a maximum. So if I'm looking at this and I'm saying, alright, I got to find two positive numbers and their sum is 190. So if I do that, what that tells me is I got two numbers. Let's call them x and y. I've got x and y, and the sum is 190. So the first thing I want to do is, they told me that the two positive numbers, the sum is 190. So I know x plus y has to be 190. I also know that the domain of x has to be 1 to 189. The reason why is because if it's a positive number, actually technically, since it's a positive number, it doesn't have, I was thinking it was integer, but in this case, it doesn't have to be an integer. So I know that it has to be larger than 0 and has to be less than 190, because if this is positive, it just has to dink it over. So can't go down to 0, can't quite get to 190. So again, I got two positive numbers, the sum is 190, and whose product is a maximum. So I want to come up with a primary equation. I say, okay, they're trying to find a product is a maximum. So I need some sort of product function. Well, the product is just the two numbers multiplied together, right? That's what a product is. So P is xy. Alright, well now what I need to do is I need to figure out a way to get P as a function of x alone. The way I'm going to do that is I'm going to use this equation. I'm going to say, oh, well that tells me y is 190 minus x. Alright, if I solve for y. Then what I can do is I can take that and I can say P of x is x times 190 minus x, which I'm going to rewrite as 190x minus x squared. So now what I do, I figured out a function of one variable, so we're almost home. With this, if you get to this point, you are way, way close to the end. So at that point we need to get its derivative, and let's go ahead and get its second derivative for good measure. Its first derivative is 190 minus 2x, which is the same thing as 295 minus x. And its second derivative is negative 2. What this tells me, since the second derivative is negative, is whatever critical value we find, it's going to be a maximum because it's always concave down. Well, the critical value here is that x is 95, because if x is 95, the first derivative is 0. That tells me that it's got to go through a maximum because it's concave down, so it's going up and coming down, so it's got to be a maximum. So that tells me x equals 95 is a likely candidate from a maximum. But let's go ahead and check the endpoints. Now, technically speaking, we can't include 0 or 190, but if we were able to, in the original function, if we were able to say P of, instead of saying 0, we could say like a really small number. Let's call it like epsilon. If we were to say that, it would be like a really small number times 190 minus a really small number. Well, that's less than that small number times 190. And again, this number is really, really, really small. So that's really close to 0. And if we did the same thing for almost 190, we would get 190 minus epsilon times epsilon, right, plugging it into here. And so that's going to be really close to 0. Either way, the point being is those values are really close to 0 versus if I plug in 95, I get 95 squared. Because I get 95 times 95. Now 95 squared, I don't know what 95 squared is. But it's a lot better than both of those. So what that tells me is x of 95 is, or if x is 95, that's a maximum. But the original problem asks for the two positive numbers. So we have to go back to this constraint here, which gets us that x is 95 and y is 95. And that's really how that's just kind of a straightforward example of how you apply these principles.